3. Atlas entered the solar system in a way that instantly alerted astronomers that something unusual was happening. Its speed, brightness pattern, and hyperbolic trajectory didn't match any local comet. Observatories across the world began tracking it, and within days, scientists realized the truth. This was only the third confirmed interstellar object ever detected by humanity. Interstellar objects are rare, not because they don't exist, but because they are incredibly difficult to detect. Most are dark, small, and fast, passing through the solar system without reflecting enough light to be noticed. The fact that Atlas was spotted at all tells us it was relatively bright when discovered, even though its behavior quickly became unpredictable. What shocked astronomers was how quickly 3I Atlas began to break apart. Unlike the stable comet nuclei we are used to in our own system, this object showed structural weakness almost immediately. As it approached the inner solar system, it fragmented, then fragmented again, until by late 2025, it had almost entirely disintegrated into a cloud of dust. This extreme fragility gives us clues about where Atlas came from. Its ices contained ratios suggesting formation in a colder, dimmer environment, likely around a red dwarf star. Such stars make up the majority of the Milky Way, meaning Atlas could be a typical representative of material formed around smaller suns. Its composition also contained more volatile compounds than we usually see in comets from our own Oort cloud. And then comes perhaps the most fascinating part. Atlas may be unimaginably old. Interstellar objects can wander for millions or even billions of years after being ejected from their home systems. During such an immense journey, cosmic radiation, gravitational encounters, and temperature extremes can weaken their structures until they become incredibly delicate, ready to crumble at even a moderate amount of heating. Because it is so fragile, Atlas offered scientists a rare chance to study material untouched since the birth of another star system. Its composition revealed insights into chemistry beyond our sun, showing that planetary systems born around different types of stars may produce comet-like bodies with very different internal structures. Most importantly, 3I Atlas proved something fundamental. Our solar system is not isolated. It is constantly crossed by interstellar debris, shards of planets, comets, and primordial material from distant worlds. If we detected 3 such objects in just a few years, the true number passing through must be dramatically higher. The story of 3I Atlas becomes even more interesting when we look at how much it differs from the 2 previous interstellar visitors. Unlike Oumuamua, which showed no coma, and unlike Borisov, which behaved like a classic comet, 3I Atlas sits between the 2 categories. It showed some activity, but the activity was unstable, fading quickly as the object began to break apart. This unstable behavior suggests that 3I Atlas had an extremely porous structure, more like compressed cosmic snow than solid rock or ice. When the sun warmed it even slightly, internal pressure changes caused cracks to grow rapidly. Instead of forming a smooth, stable tail, the object simply crumbled. Scientists believe this means it had been weakened by countless heating and cooling cycles during its long journey between the stars. One of the biggest lessons from 3I Atlas is that interstellar material is far more diverse than we ever imagined. Each object so far has been entirely different, not just variations of comets and asteroids, but unique fragments shaped by alien environments. This tells us that planetary systems across the galaxy may produce a huge range of debris, from dense rocky shards to loose, icy clusters like 3I Atlas. We also learned that objects like 3I Atlas may be far more common than our early models predicted. If we detected Oumuamua in 2017, Borisov in 2019, and 3I Atlas only a few years later, the true number passing through our solar system must be enormous. Most simply go unnoticed because they are too small, too dark, or too fast to reflect enough light for detection. Another key insight is that interstellar visitors can act as samples from other star systems, delivered naturally. The composition of 3I Atlas hints at a birthplace around a colder star, possibly a red dwarf with a thick disk of icy material. Such stars produce abundant comet-like bodies, many of which may be ejected during the chaotic early years of planet formation. But the question most people ask is whether 3E Atlas ever posed any danger to Earth. Fortunately, the answer is clear: none at all. Its trajectory placed it far from our planet, and even if it had passed closer, its fragile structure meant it would have disintegrated high in the atmosphere, producing little more than a faint meteor shower. There was no scenario in which it could impact Earth as a solid object. What 3I Atlas did reveal, though, is that interstellar objects sometimes approach without warning. Their dark surfaces make them nearly invisible until they are already inside the inner solar system. This highlights the importance of modern sky survey programs like ATLAS, Pan-STARRS, and the Vera-Rubin Observatory. Without these systems, we might miss many more alien visitors. The most impressive part of the 3I Atlas story is what it teaches us about the galaxy itself. For decades, astronomers suspected that interstellar debris must drift between stars, but 3I Atlas helps confirm that such objects are not rare exceptions. They are likely a continuous stream. Every star system ejects leftover fragments during its formation. Over billions of years, these fragments spread through the Milky Way, creating a kind of cosmic background traffic that occasionally passes through our neighborhood. The fact that 3I Atlas is extremely fragile suggests it may have spent an enormous amount of time wandering through interstellar space. Far from the warmth of any star, exposed to constant cosmic radiation, its structure weakened on a microscopic level. Ice sublimated internally, small fractures accumulated, and the body became fragile enough to fall apart rapidly once it encountered sunlight again. Some researchers even propose that 3I Atlas might have passed close to multiple stars during its journey. Each close pass could heat it slightly, causing brief periods of outgassing and stress. Over millions of years, these repeated episodes could have hollowed the object from within, transforming it into the brittle shell we saw in 2025. This would explain both its violent fragmentation and its unusual chemical composition. Another fascinating possibility is that 3I Atlas once belonged to a larger parent body, perhaps even a dwarf planet or a massive comet in another solar system. Violent gravitational interactions, such as close encounters with giant planets, can eject material into interstellar space. If 3I Atlas was once part of a larger world, then we are literally studying a fragment of an alien planet that formed under conditions wildly different from our own. Despite its dramatic breakup, 3I Atlas gave scientists a rare opportunity to examine fresh interstellar dust. As the object disintegrated, its particles spread out, allowing telescopes to analyze their spectral signatures. These observations revealed unfamiliar mixes of ices and organic compounds. Such chemistry is crucial for understanding how planets form around other stars and what materials may seed life elsewhere in the universe. One of the biggest questions surrounding 3I Atlas is how many similar objects might pass close to Earth without us ever noticing. Since this object fragmented quickly and faded from view, there is good reason to believe many others behave similarly. This means Earth is likely visited by interstellar debris far more often than we once believed. Most of it poses no threat, but some could be large enough to merit tracking. Even though 3I Atlas itself posed no danger, studying its trajectory helps improve our early warning systems. If a larger interstellar object were to head toward the inner solar system, its extreme speed would reduce the time available for detection. Learning how to track unpredictable hyperbolic paths ensures we are better prepared for future visitors, whether harmless or potentially hazardous. One of the most remarkable lessons from the passage of 3I Atlas is how much it reveals about the early chaos of planetary systems. When stars form, they are surrounded by swirling disks of ice, rock, and gas. Within these disks, young planets collide, migrate, and scatter debris in every direction. Some fragments are pushed outward with such violent gravitational force that they reach escape velocity and leave their home system forever. 3I Atlas is almost certainly one such fragment. These ejected fragments become cosmic wanderers. They do not orbit any star. They drift freely through the galaxy, heated only faintly by distant starlight. Over millions of years, their surfaces darken, their interiors cool, and their chemistry slowly changes. By the time they enter a new solar system, they carry a chemical history that formed under entirely different conditions than anything found near the Sun. When 3I Atlas disintegrated, it provided astronomers with a rare opportunity. The dust cloud it left behind acted like a natural laboratory. Telescopes analyzed the composition of the drifting particles, discovering icy grains enriched with complex organics and volatile molecules rarely seen in our comets. This suggests that alien star systems may form ices with chemical mixtures far more diverse than previously assumed. The fact that 3I Atlas fragmented so violently also challenges our understanding of comet durability. Normally, comets from our Oort cloud survive multiple trips around the Sun before breaking apart, but 3I Atlas collapsed after a single, relatively distant approach. This implies it may have contained voids, internal cracks, or layers of highly unstable ices accumulated over eons. Another intriguing detail is how quickly the brightness of 3I Atlas fluctuated during its observation period. Instead of following a smooth, brightening curve as it approached the Sun, it brightened in bursts and faded unpredictably. This suggests jets of gas escaping from fractures similar to pressure vents. Such behavior is rarely seen in local comets and points to a highly irregular structure. 3I Atlas also reinforces how essential new survey telescopes will be in the coming decade. The Vera C. Rubin Observatory, with its massive sky monitoring capabilities, is expected to discover many more interstellar objects. Even fragile ones like 3I Atlas can be detected early if the sky is monitored frequently enough. As our detection methods improve, we may learn that interstellar objects pass through the solar system far more often than anyone anticipated. What makes 3I Atlas particularly valuable scientifically is that it represents an untouched sample of a completely different star system. While meteorites offer a look into our own past, interstellar objects provide glimpses into other planetary nurseries. Studying them is like receiving ancient messages from stars we will never visit. Another important aspect of 3I Atlas is what it teaches us about planetary system evolution as a whole. Interstellar debris like this doesn't just drift randomly. It follows a story written by the gravitational interactions of its home system. At some point in its distant past, 3I Atlas may have been part of a much larger body, perhaps a proto-comet or an icy mantle of a forming planet. A close encounter with a massive gas giant could have torn it free and ejected it into interstellar space. Once an object becomes interstellar, it leaves behind every influence that once shaped it. There is no sun to warm it, no planetary body to orbit, and no stable source of heat or light. For millions, or billions, of years, 3I Atlas floated through the coldest regions of the galaxy. During that time, cosmic rays bombarded it relentlessly, breaking chemical bonds and slowly altering its surface into a dark, carbon-rich crust. When it finally entered our solar system, its surface began to heat faster than its interior. This sudden temperature difference caused pressure pockets to collapse and expand, triggering violent cracking. That's why 3I Atlas fragmented so quickly. It wasn't a simple comet break. It was the collapse of a structure weakened by unimaginable cosmic age. Despite its fragility, the dust it released held invaluable information. Some particles contained unusual ratios of carbon dioxide and ammonia, differing from what we see in comets born near the Sun. These differences suggest that the star system, where 3I Atlas originated, had a much colder outer disk, allowing ices to form that are rare in our region. It may even indicate that organic chemistry in other systems follows very different pathways. One curious possibility raised by researchers is that 3I Atlas may not have been alone. If a parent body was shattered in its original system, hundreds or thousands of pieces may have been ejected together. We may have seen just one of many fragments that spread across the galaxy. Some might already have passed through the solar system unnoticed, while others could still be on the way, invisible until they reflect enough sunlight to catch our telescopes. This leads us to the broader question: could an object like 3I Atlas pose any real danger to Earth? The answer, based on what we know, is almost certainly no. Its structure was so weak that even if it had come close to our planet, it would have disintegrated in the upper atmosphere. At worst, we would have seen a brief meteor outburst with unusual chemical signatures. The main concern is not impact risk, it's detection. Interstellar objects move faster than typical comets, giving us much less time to observe them. 3I Atlas reminded astronomers how easily such visitors can escape notice until they are already near the inner solar system. Improving our early warning systems is not about fear, it's about understanding. Each object, like 3I Atlas, is a messenger carrying secrets from distant planetary systems. Perhaps the most astonishing aspect of 3I Atlas is the reminder that our solar system is not an isolated oasis. Space between stars is not empty. It is filled with fragments like this, drifting silently across the galaxy. These objects are leftovers from the formation of countless alien worlds, each carrying pieces of history from systems we will never see up close. The fact that 3I Atlas passed through our neighborhood at all is extraordinary in itself. For scientists, observing 3I Atlas was like opening a time capsule. The dust released during its disintegration allowed researchers to study materials untouched since the birth of another star. Every particle carried chemical clues about the environment in which it formed, conditions that might be drastically different from those surrounding the early sun. This kind of natural sampling is priceless because it reveals the diversity of planetary formation across the galaxy. But 3I Atlas also served as a wake-up call. If small, fragile interstellar objects can pass so close without warning, larger and more solid ones might as well. The next visitor could be hundreds of meters across, or even kilometers in size. Detecting such objects early requires more advanced sky surveys, more sensitive telescopes, and continuous monitoring of the sky. As technology improves, the number of identified interstellar objects could rise dramatically. Still, fear shouldn't be the takeaway here. Instead, 3I Atlas teaches us something about how connected the universe really is. We often imagine our solar system as a stable, isolated place, but in reality, it is part of a much larger cosmic ecosystem. Material from distant stars flows through our space, and some of our own debris likely drifts out into the galaxy as well. We are part of a vast exchange of matter that spans light years. 3I Atlas also expands our sense of curiosity. If tiny objects can travel from star to star, what else might cross these distances? Could biological molecules survive the trip? Could fragments of early planets contain ingredients for life? For now, these questions remain open, but each interstellar visitor gives us a little more data to work with. The universe is far more dynamic and far more interconnected than we once believed. In the end, 3I Atlas reminds us that the galaxy is full of travelers. Most we will never see. Some pass silently in the dark. Others, like 3I Atlas, briefly reveal themselves before collapsing into dust. But every one of them carries a story, the story of a world beyond our own. And every time one passes through our solar system, we gain a tiny glimpse of places we may never visit, yet are forever connected to through the shared history of cosmic creation.